Hello everyone, welcome to Coffee and Notes. Today we are diving into something that trips up data scientists constantly classification metrics. Before we talk about precision and recall, we need to understand the confusion matrix, its foundation for every metric we will discuss. Every classification prediction falls into one of the four categories. Let us walk through using fraud detection as our example. True negative. You predicted not fraud, and it actually wasn't fraud. This is correct. The customer made a legitimate purchase. Your model let it through. Everyone's happy. False positive. You predicted fraud, but it is actually legitimate. This is an error. You blocked the real customer's transaction. They are frustrated. They might abandon their cart. This costs you money and trust. False negative. You predicted not fraud, but it actually was fraud. This is an error. A fraudster slipped through. You lost money to fraud. This is expensive. True positive. You predicted fraud and it was actually fraud. This is correct. You caught a fraudster. You saved money. Your fraud team investigates and confirms it. This is what you want. These four boxes TP, FP, TN, and FN are the building blocks for every metric. Accuracy, it's just TP plus TN, TP plus TN divided by total. Precision is TP divided by TP plus FP. Recall TP divided by TP plus Fn. So this is TP and this is this is precision and this is recall. Understanding these four categories is critical because different business problems care about different errors. Both FP and Fn are costly but in different ways. In cancer screening, Fn is catastrophic, missing a cancer case, while FP just means an extra biopsy. Precision. Let's talk about it. Precision answers the question when you flag something as positive, whether that's fraud, spam, or disease, what percentage of the time are you actually right? Think of it like a spam filter. You filter, the filter flags 100 emails as spam and sends them to the spam folder. We check and we find that actually 40 of those emails are actually legitimate. Work emails, bills, important updates, etc. Now this is 60% precision. You are wasting your time sifting through false alarms to find these 60 spam emails. Now the formula is simple. I am repeating it. Precision equals TP divided by TP plus FP. In other words, true positive divided by all positive predictions. All positive P and P. Let's do a concrete fraud example. Your model scores 10,000 transactions and flags the top 200 as fraud. Your investigators review those 200 and find that 150 are actually fraud. These are the true positives. TP is equal to 150. But 50 were legitimate transactions wrongly flagged. These are false positives. FP is equal to 50. Precision is equal to 150 plus 150 plus 50, that is 150 divided by 200. This is 75% fraud. What does this mean practically? It means that 75% of your fraud time is spent in investigating real fraud and 25% is wasted on false alarms. That's actually not bad. In many fraud detections, precision of 80 to 60% is considered good. You are balancing catching fraud with not overwhelming your team with false positives. High precision means when you say it's fraud, you are probably right. Low precision means you are crying wolf a lot, flagging things that turn out to be legitimate. Now let's talk about recall. Recall also answers a different question. Of all the actual fraud that exists, what percentage are you catching? Think of airport security. If 100 people pass through security carrying weapons and security catches only 80 of them, that's 80% recall. You miss 20 dangerous people. That's a serious problem. The formula? Recall equals TP divided by TP plus FN. True positives divided by all actual positives, the ones caught plus one, the ones you missed. Now let us use a medical example. In reality, 100 patients is your screening have cancer. Your test correctly identifies 85 of them as having cancer. These are the true positives. But 15 patients are told they are healthy when they actually have cancer. These are false negatives. They'll go unrated. Recall equals 85 divided by 85 plus 15, which is 85%. What does this mean? You are catching 85% of cancer cases. That sounds okay until you realize you are missing 15% people who have cancer. Those 15 people will progress without treatment. In cancer screening, missing cases is catastrophic. So you want recall as close to 100% as possible, even if it means more false positives. High recall means you are catching most of the positives. Low recall means you are missing a lot of cases. Now, remember, here's the key difference. Precision cares about the quality of your positive predictions. Rare recall cares about the quantity of actual positives you are finding. Here's the thing, you can't maximize both precision and recall at the same time. It's a fundamental trade off. Imagine you are tuning the threshold on your fraud detection model. If you set a very strict threshold, only flag transactions when you are absolutely certain they are fraud, you will have high precision. When you flag something, you are almost always right. But you will miss subtle fraud because you are being too conservative. That's low recall. On the flip side, if you set a lenient threshold, flag anything even slightly suspicious, you will catch almost all fraud. High recall. But you will also flag tons of legitimate transactions. Your fraud team will be drowning in these false alarms. Low precision. Let us break down these two extremes. Strict threshold. This is conservative approach. You only flag the most obvious fraud. Result, higher precision, few false alarms. Your fraud team doesn't overwhelm. But low recall, you miss subtle fraud. Fraudsters who are a bit clever slip through. Lenient threshold, that is aggressive approach. You flag anything remotely suspicious. Result, high recall. You catch most fraud. You're not missing attacks, but low precision, many false alarms. Legitimate customers are getting blocked. They are frustrated. You might be declining 30% of legitimate transactions to catch that last 5% of fraud. That's not a good trade. You have to choose based on business costs. Ask this question: what's more expensive in your domain? A false positive or a false negative? In fraud, it depends. Fraud positives annoy customers and cost maybe $10 in lost revenue. False negatives cost us the actual fraud amount, which could be $1,000 or more. So you lean toward higher recall, accepting some false positives. In spam filtering, false positives are very costly, missing an important work email. So you lean toward high precision, accepting that some spam gets through. Now we get to the metrics that actually matter in production. Precision at the rate K and recall at the rate K. Now here's the operational reality. Your fraud team can review 100 cases per day. That's it. Not 200, not 1000. They are humans with limited time. Your model scores 10,000 transactions daily and ranks them by fraud likelihood. Here's the question. Do you care about the overall precision across 10,000 transactions? No. You care about the precision of the top 100, the ones your team will actually review. That's precision at the rate 100. Precision at the rate K asks of the top K predictions what percentage are correct. Recall at the rate K asks of all true positives what percentage are in top K. Let's see examples. Suppose you flag top 100 transactions as fraud. 80 of them are actually fraud. So precision at the rate 100 is 80%. Your team's time is being used 80% efficiently. Now recall at the rate K asks of all actual positive what percentage are in your top K. If there are 150 fraud cases that day, okay, and 80 of them are in your top 10, top 100. Recall at the rate 100 is 80 divided by 150. It is 53%. Okay, 80 divided by 150 is 53%. You are catching 53% of the fraud. You are missing the other 47%, 70 fraud cases. Now, this paints a clear picture. Your team is working efficiently, 80% of what they review is real fraud, but you are still missing almost half of total fraud because of capacity constraints. Now, these are the metrics that drive real decisions. Do you hire more investigators to increase K? Do you tune your model to improve precision at the rate 100? Do you accept that 53% recall given your budget constraints? These are the questions that you need to answer with your business experts. Precision at the rate K and recall at the rate K align metrics with operational reality. They are what you should be tracking in production, not overall precision and recall across all predictions. Sometimes you want a single number that balances precision and recall. That's where F1 score comes in. F1 is the harmonic mean of precision and recall. Why harmonic mean and not arithmetic mean? Because the harmonic mean punishes extreme balances. If precision is 90%, suppose, and recall is 10%, the arithmetic mean would be 50%, 90 plus 10 divided by 50, which makes it sound okay. The harmonic mean, on the other hand, would be, and you can calculate, around 18%. That's a much more honest picture. So, simple thumb rule, use F1 when you care about precision and recall equally. It's a good summary metric for many classification problems. But if you don't care equally, if recall is more important than precision or vice versa, that's where F beta comes in. F beta lets you weigh one metric more heavily using the beta parameter. F 0.5 weights precision twice as much as recall. Okay, we use this when false positives are very costly. Maybe you're filtering spam and blocking a legitimate email is worse than letting spam through. F1 is equal weighting, beta equals 1. F2 weights recall F2, that is beta is equal to 2. It weighs recall twice as much as precision. We use this when false negatives are catastrophic. Cancer screening. You cannot miss cases. You will accept extra biopsies to ensure you catch every cancer case. Now, the choice of beta is a business decision, not a statistical one. It's based on the relative costs of false positives versus false negatives in your domain. Let me give you a decision framework for choosing metrics. Scenario 1. False positives are very costly. We can think of email spam filtering or loan approvals. If you block a legitimate email, you might miss something critical. If you deny a loan to a good customer, you lose business and trust. In these cases, focus on precision. You want to be right when you say positive. Use F 0.5 to weigh precision more heavily. Scenario 2. False negatives are catastrophic. Think cancer screening, airport security, or fraud that causes major losses. Missing a positive case has severe consequences. A cancer patient goes untreated. A dangerous person boards a plane. $1 million fraud goes undetected. In these cases, focus on recall. You need to catch as many positives as possible. Use F2 to weight recall more heavily. Scenario 3. You have limited investigation capacity. This is the fraud detection reality. Your team can handle 100 cases per day, period. You cannot review all flagged transactions. In this case, focus on precision at the rate K, where K equals your capacity. You want to maximize the fraud you catch within your constraint. If precision at the rate 100 is 80%, you are using your team's time well. Scenario 4, and it's not usually found in real life cases. You care about both precision and recall. General classification tasks where neither error type dominates. Maybe you are classifying customer support tickets, and both types of errors are similarly problematic. In that case, use F1 score for a balanced evaluation. What is the key? Match your metric to your business reality and costs. Now let's look at the industries when we applying these metrics. Fraud detection. The metric is precision at the rate K, where K is team capacity, maybe 100 cases per day. Why? Because you have limited investigators, you can't review unlimited transactions. What is goal? 80% precision, above 80% precision in your top daily flags. Trade-off, you accept missing some fraud to avoid overwhelming your team with false positives. You are optimizing for operational efficiency given human constraints. Cancer screening. The metric is recall. You need to catch all cases. Why? Obviously, missing cancer is life-threatening. Goal 95% plus recall, even if that means more false positives. What is the trade-off? You accept some healthy people will get extra biopsies or follow-up tests. Better safe than sorry. Spam filtering. The metric is precision, and you can make a similar, you know, argument in case of spam filtering. You want to avoid blocking legitimate email. A false positive means you miss an important message from your boss, a client, or loved one. The goal is to have 90% plus precision. In case of quality control in manufacturing, the metric to be used is F2, where beta is equal to 2. We are weighing toward recall. Why? Because defective products reaching customers damage your reputation and can be dangerous. What is the goal? High recall, acceptable precision. What is the trade-off? You accept extra inspection costs and occasionally scrapping good products to ensure defects don't reach customers. Now, can you see the pattern? The metric choices reflects what is expensive in that domain. Now let's chalk out few best practices for production. First, never use accuracy for imbalanced data. If your positive class is less than 10% of your data, like fraud, disease, defects, accuracy is meaningless. A model that predicts all negative can score 90% plus accuracy while catching nothing. Always use precision, recall, F1, or domain specific metrics like precision at the rate K. No exceptions. Second, choose metrics based on business costs. Don't just pick F1 because it's popular. Ask what's more expensive, a false positive or a false negative. In fraud, a false positive might cost $10 in lost revenue from a blocked transactions. A false negative costs you the actual fraud amount, maybe $1,000. That's a 100 to 1 ratio. Weigh your metrics accordingly. Use cost sensitive learning or tune thresholds to minimize total business cost. Third, use precision at the rate K for capacity constraints. If a fraud team can only review 100 cases daily, optimize precision at the rate 100. Don't optimize overall precision recall across all predictions. Optimize a metric that reflects operational reality. Set K based on actual human capacity. Review team size, cases, review team size times cases per person per day. If you have 5 investigators who can each review 20 cases, K is equal to 100. Fourth, track metrics over time. Monitor precision at the rate K, recall, F1 weekly. Set up automated dashboards. If precision at the rate 100 drops from 80% to 65%, that's a red flag. Now, fraud patterns have evolved. Your model is getting stale. It needs retraining. Alert when metrics drop below thresholds. Don't wait for someone to notice manually. Automate this monitoring. Calibrate thresholds for your use case. Don't use the default zero point 0.5 that most libraries go. It's arbitrary. Plot precision recall curves at different thresholds, and we will, go through precision recall curves and ROC curves in the next video. For fraud limited with limited capacity, set your threshold to flag exactly 100 transactions. That is your team's daily capacity. For cancer screening, set it low enough to achieve 95% plus recall, even if that means many false positives. Thresholds are business decisions, not model outputs. 6. Report multiple metrics to stakeholders. Okay. Don't just say the model has 85% F1 and leave it at that. That number is meaningless to a business person. Instead, translate it like this. Of all the 100 transactions, 80 are actual fraud. That's precision at the rate 100 of 80%. We are catching 53% total fraud. That's a recall of 53%, which saves us approximately 500,000 per month while keeping our team's workload manageable. That's how you present to the business guys. See the difference? You have connected metrics to business impact, team operations, and dollar amounts. That's what stakeholders need to hear. Now, let me walk through the mistakes I see constantly. Mistake number one, using accuracy on imbalanced data. Your fraud data set is 1% fraud, 99% legend weight. Someone builds a model. It predicts everything as not fraud, and they reports 99% accuracy. They are proud. Don't be that person. Check class distribution before choosing metrics. For imbalanced data, accuracy is a lie. Mistake 2, ignoring operational constraints. You optimize for F1 and achieve zero point 0.9. Great, but your model flags 1000 transactions daily, and your team can review only 100. All that high F1 means nothing if the top 100 are garbage. What matters is precision at the rate 100, not overall F1. Optimize for reality, not textbook metrics. Mistake number 3, using zero point 0.5 as the default threshold. Someone builds a model using zero point 0.5 because that's the default and deploys. That threshold is arbitrary. It has no connection to your business. In cancer screening, you might use zero point 0.2 to catch more cases. In spam filtering, you might use zero point 0.8 to avoid blocking legitimate email. Calibrate thresholds based on costs, not defaults. Mistake 4, forgetting the confusion matrix. Someone reports we have high precision. You assume success. But what they did was be ultra conservative. They flagged only 10 super obvious fraud cases, achieving 100% precision. Meanwhile, they don't miss 90 subtle fraud cases. You need to check all four quadrants: TP, FE, and FN. Don't just trust a single metric. These are a few key takeaways, a costs of the summary of sorts of the entire session. I'm skipping them to keep the video length short. And that's it for today. We have covered why accuracy lies, what precision recall actually measure, and the production metrics that matter. Precision at the rate K and recall at the rate K. In the next video, we are going visual. I'll show you ROC curves and AUC and how to choose the perfect threshold by looking at the entire precision recall trade-off at once. It's a powerful tool for understanding your model's behavior. If you found this helpful, hit that like button and subscribe to Coffee and Notes for more practical machine learning content. Drop your questions about classification metrics in the comments, especially if you're dealing with imbalanced data in production. I read every comment. Thanks for watching, and I'll see you in the next one. Thank you.